Though the Sun lies 93 million miles 149 million kilometers from Earth, its unceasing activity assures an impact on our planet far beyond the obvious light and heat. From a constant stream of particles in the form of solar wind to the unpredictable bombardment from solar flares and coronal mass ejections, Earth often feels the effects of its stellar companions. Less noticeable are the sunspots crossing the solar surface, though they are related to the more violent interactions. All of these fall under the definition of space weather. Studying the surface of the Sun can reveal small, dark areas that vary in number and location. These sunspots, which tend to cluster in bands above and below the equator, result from the interaction of the Sun's surface plasma with its magnetic field. According to NASA, sunspots are the most visible advertisement of the solar magnetic field. Sunspots are cooler regions that cap some of the intense energy below them. Here's how they form. The material at the solar equator travels significantly faster than the material at the poles. The magnetic field lines become warped. When the magnetic field is strong enough, and twisted enough, jet streams of flowing currents create ropes of magnetism. Most of the rope, or filament, lies inside the Sun, but part of it may break through the visible layer, where it is viewed in the form of two sunspots. The pair are polar opposites. Literally think of them as magnetic north and south, with the rope acting as the magnet in between. Photos. Sunspots on Earth's closest star. Credit carltatespace.com. At temperatures of 3,800 Kelvin 6,380 degrees Fahrenheit or 3,527 degrees Celsius, sunspot temperatures are nearly 2,000 K 3,140 F 1,727 C, less than the rest of the Sun. But don't let the numbers fool you. If a single sunspot stood alone in the night sky, it would be 10 times brighter than the full moon. Similarly, sunspots might seem small when compared to the 865,000-mile 1.392 million kilometers diameter of the Sun, because they typically cover less than 4% of its visible disk. However, ranging from 1,500 miles to 30,000 miles to 50,000 km in size, they can reach the width of the planet Neptune, the smallest of the gas planets. But with a lifetime of anywhere from a few days to a few weeks, sunspots are far less permanent. Sunspots do not appear in random locations. They tend to be concentrated in two mid-latitude bands on either side of the equator. They begin appearing around 25 to 30 degrees north and south of the center. As the solar cycle progresses, new sunspots appear closer to the equator, with the last of them appearing at an average latitude of 5 to 10 degrees. Sunspots are almost never found at latitudes greater than 70 degrees. According to NASA, it takes approximately 11 years for the Sun to move through the solar cycle that is defined by an increasing and then decreasing number of sunspots. As it reaches the close of a cycle, new sunspots appear near the equator, while a new cycle produces sunspots in higher latitudes. The cycles overlap. Sunspots from the previous cycle can still develop even after sunspots from the new cycle appear. So solar scientists have a very difficult time saying exactly when one cycle ends and the next begins. As of early 2017, solar cycle 24 was approaching solar minimum. The 11-year cycle began in January 2008 and peaked in 2013, the weakest solar maximum in 100 years, according to NASA. Despite the low level of activity, one of the largest sunspot regions ever was observed in November 2014, reaching approximately the size of Jupiter. Scientists measure the activity of the Sun by keeping track of the number of sunspots appearing on its surface. Since the invention of the telescope, sunspot counts have been relatively constant. In 1849, astronomers at the Zurich Observatory began observing and counting sunspots on a daily basis. The Solar Influence Data Analysis Center in Belgium and the U.S. National Oceanic and Atmosphere Administration are responsible for monitoring sunspot activity today. This snapshot from NASA's Solar Dynamics Observatory shows a stunning prominence associated with a September 8, 2010 solar flare. Credit NASASDO. The high magnetic fields in the sunspot-producing active regions also give rise to explosions known as solar flares. When the twisted field lines cross and reconnect, energy explodes outward with a force exceeding that of millions of hydrogen bombs. The Sun's worst solar storms in history. Temperatures in the outer layer of the Sun, known as the corona, typically fall around a few million Kelvin. As solar flares push through the corona, they heat its gas to anywhere from 10 to 20 million K, occasionally reaching as high as 100 million K. According to NASA, the energy released in a solar flare is the equivalent of millions of 100 megaton hydrogen bombs exploding at the same time. Because solar flares form in the same active regions as sunspots, they are connected to these smaller, less violent events. Flares tend to follow the same 11-year cycle. At the peak of the cycle, several flares may occur each day, with an average lifetime of only 10 minutes. The enormous sunspot of 2014 fired off several powerful solar flares. The largest, X-class flares, have the most significant effect on Earth. They can cause long-lasting radiation storms in the upper atmosphere, and trigger radio blackouts. Medium seismic-class flares can cause brief radio blackouts in the polar regions and the occasional minor radiation storms. C-class flares have few noticeable consequences. Solar flares: a user's guided infographic. When the energized particles exploding from solar flares race toward us, they arrive in only 8 minutes. Astronauts in space risk being hit by these hazardous particles, and manned missions to the Moon or Mars must take this danger into account. Everyone else is shielded by the Earth's atmosphere and magnetic field. Sensitive electronic equipment in space can also be damaged by these energetic particles. Absorbing X-rays affects the atmosphere. The increase in heat and energy result in an expansion of the Earth's ionosphere. Man-made radio waves travel through this portion of the upper atmosphere, so radio communications can be disturbed by its sudden unpredictable growth. Similarly, satellites previously circling through vacuum-free space can find themselves caught in the expanded sphere. The resulting friction slows down their orbit, and can bring them back to Earth sooner than intended. Despite their size and high energy, solar flares are almost never visible optically. The bright emission of the surrounding photosphere, where the sun's light originates, tends to overshadow even these explosive phenomena. Radio and optical emissions can be observed on Earth. However, since X-rays and gamma rays fail to penetrate the atmosphere, only space-based telescopes can detect their signatures. Sometimes, it's not activity but a lack of it that can release deadly particles toward Earth. The interactions of hot plasma of the corona with the sun's magnetic field can create coronal holes, which permit plasma to stream rapidly from the sun. The effects linked to coronal holes are generally milder than those of coronal mass ejections, but, when the outflow of solar particles is intense, can pose risk to satellites in orbit, NASA said in a statement. In 2017, scientists were able to link high-energy gamma-ray bursts to solar flares for the first time using NASA's Fermi Gamma-Ray Space Telescope and its Solar Terrestrial Relations Observatory stereo. These particles must travel some 300,000 miles 500,000 kilometers within about 5 minutes of the eruption to produce this light, study co-author Nicola Omode, a researcher at Stanford University in California, said in a statement. This still from SDO caught the action in freeze-frame splendor when the sun popped off two events at once. January 28, 2011. A filament on the left side became unstable and erupted, while an M1 flare mid-sized and a coronal mass ejection on the right blasted into space. Credit NASASDOGSFC. The magnetic field lines that twist up to form solar flares occasionally become so warped that, like rubber bands under tension, they snap and break, then reconnect at other points. The gaps that form no longer hold the sun's plasma on its surface. Free, the plasma explodes into space as a coronal mass ejection CME. Stunning photos of solar flares sunstorms. It takes several hours for the CME to detach itself from the sun, but once it does, it races away at speeds of up to 1,000 kilometers per hour or more than 7 million miles per hour. One of the fastest recorded CMEs, registered in 2012, traveled about 6.48 million to 7.92 million miles per hour, 10.43 million and 12.75 million kilometers per hour. Seeing a CME this fast really is so unusual, Rebecca Evans, a space scientist at Goddard's Space Weather Lab, said in a statement. And now we have this great chance to study this powerful space weather, to better understand what causes these great explosions, and to improve our models to incorporate what happens during events as rare as these. The cloud of hot plasma and charged particles may be up to 100 billion kilograms 220 billion pounds in size. As with solar flares, if the CME is aimed in our direction, it takes the particles 8 minutes to reach Earth. However, the particles take anywhere from 1 to 5 days to travel the distance to our planet. The solar wind, a constant stream of charged particles ejected by the sun, acts on the cloud like a current on a boat. Faster CMEs feel the drag of the wind and slow down, while those with low initial velocities speed up. The northern lights are more formally known as auroras, and are caused by interactions between the solar wind and the Earth's magnetic field. Credit Carl Tate, Space.com contributor. Aurora's northern lights. When the energy from a solar storm reaches the vicinity of Earth, charged particles in our planet's upper atmosphere interact with air molecules to create auroras. These northern lights, as they are also called, can be fantastic displays of color. The solar wind also generates a near-constant but less spectacular display. Many solar storms aren't aimed toward us. At the high point of the solar cycle, the sun may produce as many as 5 centimeters in a given day. Even at the low point, it averages 1 a day. The spherical shape of the sun means that most of them miss the Earth completely. In fact, we can't even observe all of the ejections. Those emerging directly opposite our planet are undetectable. However, when the sun does eject a cloud of plasma and gas directly toward us, the incoming matter seems to surround the sun. Much like a baseball falling from the direction of the sun can seem to grow larger and dwarf the star, the so-called halo. Coronal mass ejection can appear to overshadow its source. Such ejections cause the most problems for the people on Earth. Like solar flares, CMEs bring an increase in radiation to astronauts and electronics in space. But unlike flares, they also bring charged particles of matter that interact with the field surrounding our planet. The results vary depending on the size, speed and magnetic strength of the particles. On February 13 at 1738 UT, Sunspot 1158 unleashed the strongest solar flare of the year so far, an M6.6 category X-ray radiance magnitude blast. NASA's Solar Dynamics Observatory recorded an intense flash of extreme ultraviolet radiation. The source of this activity, Sunspot 1158, is growing rapidly. Credit NASASDO. When the particles reach the Earth's magnetic sphere, they stretch and distort. Much like a tree in a strong wind, the day side, the first side affected, is compressed, while the night side is stretched out like a tail. When it reconnects on the night side, it releases the energy found in a bolt of lightning. While lightning lasts on the order of microseconds, however, the magnetic storm created lasts far longer. It races back toward Earth's upper atmosphere. The sudden increase in power can damage sensitive electronic equipment. Power transformers can overload, causing long-lasting blackouts. Long metal structures like oil and gas pipelines can carry currents, which can enhance their corrosion over time and lead to devastating effects if proper safety measures are not in place. The resulting variations in the ionosphere can disrupt GPS signals, giving inaccurate readings. On September 1, 1859, Richard Carrington and Richard Hodgson, both amateur English astronomers, independently made the first observations of a solar flare, one that resulted in the largest geomagnetic storm ever recorded. Auroras, which normally occupy the polar regions, were visible in tropical latitudes. Telegraph operators reported being shocked, literally, by their instruments. Even after unhooking them from the power supply, messages could still be transmitted, powered by the currents in the atmosphere. The so-called Carrington event would be far more devastating if it happened today, given the greater reliance on electronics and the expanded power supply. However, thus far, it is the strongest storm yet recorded, though scientists think that a powerful CME from 2012 that missed Earth would have wreaked havoc for several years had it collided with the planet. I have come away from our recent studies more convinced than ever that Earth and its inhabitants were incredibly fortunate that the 2012 eruption happened when it did. Daniel Baker at the University of Colorado, who led a study of the storm in space weather, said in a statement. A Atlas V rocket carrying NASA's Solar Dynamics Observatory satellite rolls out to its Space Launch Complex 41 launch pad at Cape Canaveral Air Force Station in FLA, for a planned February 10, 2010 launch. Credit Pat Corkery, United Launch Alliance. NASA is currently implementing Project Solar Shield to provide warnings to vital systems after an Earth-affecting CME occurs. This allows satellites and power transformers to be shut down if necessary for a short period of time. The result is a short-term, controlled blackout rather than a longer one caused by the destruction of vital equipment. Amazing new sun photos from space. Similarly, several satellites keep the entire sun under constant observation. NASA's Solar Heliospheric Observatory SOHO spacecraft studies the sun, while the Solar Dynamic Observatory SDO focuses on solar atmosphere. Advanced Composition Explorer samples particles from the sun as they stream toward our planet. In November 2016, the National Oceanic and Atmospheric Administration launched the latest of its geostationary operational environmental satellites, GOES-16. Since 1975, the GOES satellites have monitored Earth's atmosphere along with solar activity. These programs will help bring a greater understanding of the subject of space weather on Earth. In 2015, the United States announced its plan to deal with space weather. The National Space Weather Strategy outlines a framework to better understand, predict, and recover from space weather-related events, while the National Space Weather Action Plan specifies activities to reach these broad goals. The efforts undertaken to achieve the objectives of this strategy will establish a national approach to the security and resilience in the face of our improved understanding of the seriousness of the space weather risk, and the steps we must take to prepare for it. Suzanne Spalding, Undersecretary for the U.S. Department of Homeland Security's National Protection and Programs Directorate, said during an event hosted by the White House Office of Science and Technology Policy (OSTP).